In this video, we're going to do two application problems. One important application using vectors occurs during navigation. We have a jet airliner with a velocity due east 500 miles per hour, and that is in still air. But of course, we know that there's other air blowing around that may affect the way this jet airliner flies. So there's a 70 mile per hour tailwind, and it is blowing in a direction 60 degrees north of east. So the airplane holds its compass heading due east, but because of the wind, that's going to change the ground speed and the direction. What we want to know is what are the new ground speed and direction. Here I've brought in a picture. We have 500 miles per hour heading due east. So 500 miles per hour is going to be a longer vector than this tailwind, which is pushing on it 70 miles an hour. We are heading in a direction, the wind is 60 degrees north of east. So that means this wind, in order to get to that wind vector, we traveled up 60 degrees or down 30 degrees to the east of north. Either are the same angle. This picture is not drawn to scale, but notice I did draw my 500 quite a bit longer than my 70. For this problem, I'm going to let U represent the velocity of the airplane alone, and V is going to represent the tailwind. Well, we know the magnitude of U is 500. We also know the magnitude of our tailwind, V, is 70. The velocity of the airplane with respect to the ground is given by magnitude and direction of that resultant. The resultant being the sum of U plus V, not just the sum of their magnitudes. Now, the positive x-axis in our diagram is representing east, and 90 degrees is representing north. So as we think about representing these vectors in component form, U is 500 in the x direction, 0 in the y direction. V, we have that magnitude 70, and then we're going to use cosine of 60 for the horizontal portion, and 70 sine of 60 gives us our vertical portion. Remember, cosine is always associated with x and sine is associated with y. So that can be simplified a little bit because we know what cosine and sine of 60 are. Cosine of 60 is 1/2, so 70 times 1/2 gives us 35. Sine of 60 is √3/2, or 35 √3 when we simplify. Therefore, the sum of U plus V is the sum of my x's, or my horizontal components, and my y's, my vertical components. So I have 500 plus 35 gives me 535, and 0 plus 35 √3 is 35 √3. Now, if we want to find the magnitude of U plus V is the square root of the sum of the squares of each component. So I've got 535 squared plus 35 √3 squared. And this isn't a nice clean number, so I'd type that into my calculator, and I get 538.4. Now, we also need the direction. This has been the magnitude. So we know that new speed, or the new velocity, is 538.4 roughly miles per hour, right? That 70-mile-an-hour tailwind has increased that original 500-mile-per-hour velocity about 38.4 units. So, dealing with vectors, again, we need a magnitude and a direction. One thing for us to think about when we've got our sum, u plus v, remember we have an x and a y component. So if we want to relate x and y with theta, we go to some of our trig definitions. And most commonly, the one we use is tangent theta is y over x, sine over cosine, or opposite over adjacent. Modifying that to solve for theta, I would have theta equals tangent inverse of y over x. So theta is tangent inverse of my y value, 35 root 3, over my x value, 535. And typing this into my calculator, making sure that I'm in degree mode, I get roughly 6.5 degrees. Therefore, we can say we have a new ground speed of 538.4 miles per hour, and then we have a new direction. We are not headed due east. We are headed 6.5 degrees north of east. So remember, this is east. The tailwind was blowing us that way. We have traveled 6.5 degrees up. So this is our new trajectory. All right, I'm going to do one more example in this video. In this example, we have a 75 Newton weight suspended by 2 wires. We'd like to find the forces acting on both wires. So in this diagram, we can see we have our 75 Newton weight, and then force 1 is pulling up, making a 55-degree angle with the ceiling. Force 2 is pulling up, making a 40-degree angle with the ceiling. If we know some of our properties from geometry, we have alternate interior angles. If I were to draw another parallel line here, because I know this is 40, I know that angle is 40. We're going to do this a little bit differently than you may have done it in your trig class. In trig, we might have referred to that angle from our standard position, or 0, as 125 degrees. 125 plus 155 gives us that 180. In this case, we're going to think about that as just being a 55-degree angle in quadrant 2. So the first thing I want to do here is represent my two forces, force 1 and force 2, as component vectors. Well, force 1, and if we think about putting a coordinate plane in here, we've got 0. Force 1 being in quadrant 2 can be represented as a horizontal and a vertical component. Because we're in quadrant 2, we would have negative magnitude of force 1 times cosine of that angle, 55, cosine goes with x, and then my y value is positive, or sine is positive, so I'd have F1 magnitude sine of 55. For my other vector, force 2 here, force 2 being in quadrant 1, these are both going to be positive, so I've got the magnitude of force 2 times cosine of that angle, 40, times the magnitude of force 2 times sine of 40. So these are my two component vectors for the force. If we think about the vector, or how we would represent the vector of this weight coming down, we have 0 horizontal movement and negative 75 for my vertical movement. In order for this system to be in balance, I know that the sum of my two forces acting up must be 0, positive 75. So what we can say is that we know that force 1 plus force 2 needs to equal this vector 0, 75. And what we see here is the sum of these two resultant, or the sum of these two vectors giving us the resultant. This leads to a system of equations. We have our x components, the negative magnitude of force 1 times cosine of 55, plus the x component for force 2, the magnitude of force 2, times cosine 40. Those need to sum together and equal the x component of my resultant, 0. And then similarly with the y, so we'd have the magnitude of force 1, sine of 55, plus magnitude of force 2, sine of 40, and those would equal 75. At this point, we just need to solve a system of equations for my two variables, force 1 and force 2. You could think of them as being an x and a y, and these are just my coefficients. So what I'm going to do is I'm going to isolate force 2. I'm going to take this first equation and rearrange it. And if I do that, I can say, well, force 2 times cosine 40 is going to equal force 1 times cosine of 55. And I could divide by cosine 40. So that would really give me force 1 cosine 55 divided by cosine of 40. So all I've done is take this equation, I added this term to the right side and divided by cosine 40. I've now isolated force 2. Since I know what force 2 is, I can take force 2 and plug it into the other equation for force 2, and then I'll have an equation with only one variable, force 1. So this gives me, and I'm leaving my absolute value bars off now at this point because I know I'm going to get a positive value and it just cleans up my notation. But I've got force 1 times sine of 55 plus force 2. Force 2 we just said is force 1 times cosine of 55 over cosine of 40 times sine of 40. So this equals 75. All I've done is I took this and I plugged that in right there. Now, sine over cosine is tangent, so I'm going to use that to clean this up. Force 1 sine of 55 plus force 1 cosine of 55 sine over cosine tangent of 40 equals 75. If I factor out a GCF of force 1, that leaves me with sine of 55 plus cosine of 55 times tangent 40. Or now we can say force 1 equals 75 divided by the quantity sine 55 plus cosine 55 times tangent 40. If I evaluate that in my calculator, I get approximately 57.67 newtons. So that means force 1 is acting upwards at that angle of 55 degrees or 125 degrees, depending on how you consider it. with a positive pull of 57.67 newtons. Now, because I know force 1, I have this exact value for force 1, I can take it and plug it in right up here to force 1, and that would give me force 2. So I'm going to take this, multiply it by 55, distribute a cosine 40 through the denominator. So force 2 is 75 times cosine of 55 over cosine of 40 times sine of 55 plus cosine of 55 times tangent of 40. Or as it's written in your book, 75 cosine 55 over cosine 40 sine of 55 plus cosine 55, and cosine 40 times tangent 40 is sine 40. And that value is approximately 43.18 newtons. Therefore, my force vectors, force 1, recall we said was negative force 1 cosine 55, force 1 sine of 55. Plugging that value in, we get approximately negative 33.08, comma 47.24. Running out of space. And force 2 was force 2 cosine 40, force 2 sine 40. Plugging that value in, we would get approximately 33.08 and 27.76. So these represent the vectors of the forces acting upward in component form. As always, please email me if you have any questions.